Counter is the circuit which counts the pulses. It has got mainly two types, synchronous counter and asynchronous counter. Asynchronous counter is also known as a ripple counter. We are going to focus on synchronous counter in this tutorial. Synchronous counter is also divided into two parts, up counter and down counter. The synchronous counter improves the speed of operation because all the flip-flops in the synchronous counter are clocked simultaneously, and it doesn't happen in asynchronous counter. The asynchronous counter has the advantage of simplicity, but their speed is low because of the ripple action. We can design synchronous counter for any count sequence. We can design up counter from 2 bit to n bit, as well as we can design down counter from 2 bit to n bit. We will see how to design synchronous counter in the next slide. These are the steps to design synchronous counter. We have 5 steps in all to design synchronous counter. Step 1 is determine the number of flip-flops required. Step 2, write the count sequence and draw the state transition diagram. Step 3, determine the flip-flop inputs from excitation table. Step 4, prepare K-maps for each flip-flop input and simplify. And last step, connect the circuit using flip-flops and other gates corresponding to minimized expressions. We will see each step thoroughly in the next slides. We will design 3-bit up counter. It is also known as mod 8 up counter. We will follow the step 1, which says determine the number of flip-flops required. Since we are going to design 3-bit up counter, so we are going to need 3 flip-flops. The relation between bits and flip-flops is like this. If we want to design 2-bit counter, then we need 2 flip-flops. Since we are designing 3-bit counter, we need 3 flip-flops. If we increase the bits, flip-flops will increase. If it is 4-bit, it will be 4. If it is 5-bit, it would be 5. Synchronous counters can be designed with the help of either SR flip-flop or D flip-flop or JK or T flip-flop. But normally, counters are designed with JK and T flip-flop. We will see that in the next slide. Now we will see the step 2. It says that write the count sequence and draw state transition diagram. Now we are going to use 3 flip-flops for the counter. We are going to have 3 outputs. In this table, column headings are given as Q3, Q2, Q1, which indicate the output of each flip-flop. Since we are designing up counter, that means counter will be counting in the upward direction. The count sequence of the counter would be like this, and this count sequence is shown in the table. First count will be 0, 0, 0. Next one will be 0, 0, 1. Then 0, 1, 0. Then 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. So mod 8 counter or 3-bit counter will count maximum up to 111, and once that stage is reached, that is this stage, then counter will again go back to the first state, that is 000, and cycle repeats. The meaning of state transition diagram is, that is, first state of the counter is 000. Next state we want it to be 001. Then next we want it to be 010. Then next we want it to be 011. Then next we want it to be 100. Next we want it to be 101. Then next it would be 110. next it would be 1 1 1, and after that 1 1 1 it will go back to the original state, that is 0 0 0. So this is what is the state transition diagram for 3-bit up counter. Now next step is step 3, where we have to determine the flip-flop inputs from the excitation table. We are going to design the counter with the help of both the flip-flops, that is JK and T flip-flop. So first we will see the construction of table with the help of JK. This is the excitation table of JK flip-flop. I have made one video on excitation table of JK flip-flop. I request you to watch that video. In that video, we have developed the excitation table of JK flip-flop. What this table is showing is that in the first column, these are the states, that is from 0 to 0. That means present state is 0 and then it is becoming next state as 0. If you want this transition, then J has to be 0 and K is don't care. If our present state is 0, if you want it to be 1, then J has to be 1, K can be anything, that is don't care. Similarly, if our present state is 1, next state is 0, then this is what is required. X, that is J is don't care and K is 1. And finally, if our present state is 1 and next state is 1, then J can be anything, that is don't care, and K is 0. Depending on that, we are going to now determine the inputs of the flip-flop. Now, this is what is the table which we are going to feed. Now, Q3, Q2, Q1, which are shown in the first 3 columns, these are our present states. So, this particular 3 columns are the present state. And these 3 columns, they are the next state. What I mean to say, we are going to use 3 flip-flops, and what we want as the first state is 0 0 0. Then next sequence I want 0 0 1, then 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, and 1 1 1. That is what is binary sequence we need when we design the counter. So this is what is my present state. When present state is 0 0 0, when I give the clock pulse, my next state should be 0 0 1. When my present state is 0 0 1, my next state is 0 1 0. When my present state is 0 1 0, then my next state is, that is 0 1 1. So similarly, I can write now here as 1 0 0, here as 1 0 1, here it is 1 1 0, here it is 1 1 1. And once I reach 1 1 1, that is the final count, I will go back to the 0 0 0. This is my next state. Now once I know what is present state and what is next state, I can fill the columns of J and K, because I am going to use 3 flip-flops. So we are going to have inputs like J3 K3, J2 K2, and J1 K1. Now how it is to be filled, see here. My present state is 0 and my next state is 0, that is for Q3. That is, suppose I want to write it for now J3, present state is 0, next state is 0, so 0 to 0, J is 0. And for 0 to 0, K is don't care. So I will write here don't care. Now my present state is 0 and my next state is 0. Again I will write it as, that is 0 and don't care. Present state is 0, next state is 0, it is 0 and don't care. Now present state is 0, next state is 1. So 0 to 1 is J1 and K don't care. Now present state is 1 and next state is 1. So this is don't care and 0. Now present state is 1, next state is 1, it is don't care and 0. Here it is again 1 and 1, so that is don't care and 0. And finally, present state is 1 and next state is 0. So it is this one, that is don't care and 1. So I have decided the input J3 and K3 from the excitation table. Similarly, we can fill the other columns, that is J2, K2, J1, K1. T3, T2, T1, these are the column for T flip-flops that we will fill in few minutes. Now, if I want to fill now J2, K2, then I will go for this. So Q2 here and Q2 here. So 0 to 0, it is this one. Then we're having 0 to 1. 0 to 1 is 1 and don't care. Then we are having 1 to 1, that is don't care and 0. So if you see and if you go on filling accordingly, what we will get is, we will get next will be don't care 1, then we will get 0 don't care, then we will get 1 don't care, then we will get don't care 0, then we will get don't care 1. Similarly, you go on filling for J1 and K1, you will get 1 don't care 1, 1 don't care 1, 1 don't care 1, 1 don't care 1. So we have determined the flip-flop inputs from the JK excitation table. This is what is for construction of counter with the help of JK. If I want to design with the T flip-flop, then what I have to do, I have to go for the excitation table of T flip-flop. Now this is what is the excitation table of T flip-flop, which shows that when it is present state is 0 and next state is 0, it is 0. Then when it is 0, present state and next state is 1, it is 1. For 1 to 0, it is 1 and 1 to 1, it is 0. For this again, one video is made. Please watch that video. Now if I want to fill now these three columns, it is very easy. Now my present state is 0 and my next state is 0, T is 0. If my present state is 0, next state is 0, then T is 0. Then my present state is 0, next state is 0, T is 0. Present state is 0, next state is 1, then it is 1. Present state is 1, next is 1, then it is 0. Then present state is 1, next is 1, it is 0. Present state is 1, next is 1, it is 0. Present state is 1, next is 0, then it is 1. Similarly, for T2, if I want to fill the column, present state is 0, next state is 0, then 0. Present state is 0, next state is 1, then it is 1. Present state is 1, next state is 1, then it is 0. Likewise, we can go on filling the columns and we will get last as 1 here. Now if you want to fill the T1, again what I will do, present state is 0, next state is 1. So it is 1. Present state is 1, next state is 0. So it is 1. Present state is 0, next state is 1. It is 1. Like that, if you go on filling it, it would be like this. So this is what is the table made by using JK excitation table and T excitation table. And from this table, we will now prepare the K map and we will simplify it in the next slide. Now we will go to the step 4 where we will prepare the K map for each flip-flop input and simplify. In last slide we have developed the table. I have copied that table from the last slide into this slide. From this table we will fill the K map for each input. Before filling the K map, Let us first write the decimal equivalent of each input here so that it would be easy for us to fill the K-map. So first it is 0, 0, 0. It is, I am writing 0 here. This is 1, this is 2, this is 3, this is 4, this is 5, 6 and 7. Now we are having 6 inputs in all, that is J3, K3, J2, K2, J1 and K1. So we will draw the K-map for each input separately. Now this is the K-map, we are drawing it for J3. Now see here how it is done. So this is, I am writing here Q1 and this is Q3, Q2. Okay, this is 0, 0, 0, 1, 1, 1, 1, 0 and this is 0, 1. Now if in K-map this block 0, 0, 0, its decimal equivalent is 0, this would be 1, this would be 2, this would be 3, this would be 4, 5 and this is 6 and 7. Now you can see for J3, when it is 0 decimal, that is 0, 0, 0, J3 is 0. For it is, here it is 0. For 1, J3 is 0. For 2, J3 is 0. For 3, J3 is 1. And for 4, 5, 6, 7, J3 is don't care. Here it is don't care everywhere. If we simplify the K-map for J3 now, we will get a pair from this. So answer for J3, we will get it as Q1, Q2 after simplification. Similarly, we will go for now K3. This is my Q3, Q2 or Q2, Q3. This is my Q1. This is 0, 1. This is 0, 0, 0, 1, 1, 1, 1, 0. And these are the decimal numbers for each block. So this is 2, this is 3, this is 4, 5, 6 and 7. So for 0, what is K3? K3 is don't care. For 1, what is K3? K3 is don't care. For 2, what is K3? It is don't care. For 3, it is again don't care. For 4, 5, 0, 0, 6, 7, it is 0, 1. Now here K3, if you want to solve it, again we can make a pair out of it. So K3, I can write it as Q1 and Q2, that is Q1, Q2. Similarly, we can make table for J2. This is Q3, Q2, this is Q1. Now you will get it. This is 1, 0, 1, 2, 3, 4, 5, 6 and 7. We'll fill the columns for J2. This is 0 here. This is 1 here. This is don't care. This is 0. This is 1. This is don't care. Now if you see it properly, here we can make quad out of it. So J2 is equal to Q1. Similarly, for K2 we will write this is Q3, Q2, this is Q1, and if you fill the K2 column, we will get K2 as, after filling, this is don't care. Here it is, we will get it as this. So here we can make again a quad out of it, and answer for K2 is equal to Q1. If you go for Now J1, this is Q3, Q2, this is Q1, and if you fill the table, it would be like this. Here it would be 1, 1, 1, 1, and here it is don't care everywhere. So we can make a quad out of it, sorry, octet out of it, and you will get J1 as a 1. And remaining only is now K1. I will write K1 here. This is Q3, Q2, this is Q1, and if you fill the table, you will get it like this. And again, we can make one octet out of it. So answer for K1 is 1. So we have decided the inputs from the K map after the simplification. And next step would be the final step of constructing the counter. Now we will go for the final step, that is step number 5, where we are going to connect the circuit using flip-flops and gates corresponding to the minimized expressions. We will write the expressions which we got in the previous slide. We got J3 is equal to Q1 Q2. We got K3 is equal to Q1 Q2. We got J2 is equal to Q1. We got K2 is equal to Q1. We got J1 is equal to 1 and K1 is equal to 1. Now 3 flip-flops are shown having inputs JK and outputs as Q. We know each flip-flop has got preset, terminal and clear, so that we will write here. So this is preset, clear, this is preset, this is clear. Each has got the clock input. So this is negative edge triggered flip-flop. This is again negative edge triggered flip-flop. So these lines of the clock pulse are taken together and we are connecting them to the clock main terminal. Now we can see J3 is equal to Q1 Q2. So this is my J3 and Q1 and Q2 are here. What I am doing, try to understand. So this is Q1, this is Q2. They are ANDed to give the output Q1 Q2, and that is connected to J3. Now K3 is again Q1 and Q2. That means this output I can take straight away from this. So this is my K3. J2 is equal to Q1. So J2 is equal to Q1. So Q1 is this line. So I can take that point from here and it is connected here. So this is my Q1. K2 is again Q1. So this Q1 is taken down and it is connected to K2. J1 is 1. So J1 is written as 1 and K1 is 1. So K1 is written as 1. So this is the mod 8 up synchronous counter or 3-bit up synchronous counter using. Now we will construct the synchronous mod 8 up counter with the help of T flip-flop. I have copied this table from the step number 3. As usual, we will write the decimal equivalent for all the inputs here so that it would be easy for us to put the values in the K map. We are having now 3 inputs T3, T2 and T1, so we will be making 3 K maps for that. Now this K map would be for T3. Now this is your Q3, Q2, this is your Q1, this is 0, 0, 0, 1, 1, 1, 1, 0, this is 0, 1. These are the numbering of the squares. This is 4, 5, 6 and 7. If you see the T3, so this is 0, 1 and 2. So all are 0. Now 3 is 1, 4, 5, 6, 0 and 7 is 1. So we can make one pair out of it. So T3 is equal to Q1, Q2. If you go for T2, now same process will follow. This is Q3, Q2. This is Q1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. These are the square numbers. This is 6 and 7. And if you put the values, what you will get it for T2 as 0, 1. Here it is 0, 1, 0, 1, 0, 1. So we will get quad out of it. So T2 will be equal to Q1. Now finally we will write it for T1. So this is Q3, Q2. This is Q1. This is 0, 1. This is 0, 0, 0, 1, 1, 1, 1, 0. These are the numbers for squares and we will put the values there. So all are 1. So we can make one octet out of it. So T1 is equal to 1. So now from these three inputs we can construct the counter with the help of T flip-flop in the next slide. Now we will write the minimized expressions for T3, T2 and T1 which we got in the previous slide. So T3 is equal to, we got it as Q1, Q2. T2 we got it as Q1 and T1 is equal to 1. Now these are the three T flip-flops. We are having preset for each and clear for each flip-flop and then clock for each flip-flop. And these clocks are tied together and connected to the main clock terminal. Now T3 is equal to Q1, Q2. So this is my Q2, this is my Q1. So this is taken here, this is taken here. They are ANDed. So output of this is Q1, Q2 and that is connected to T3. T2 is equal to Q1. So I am taking Q1 from this and it is connected to this. So this is my Q1 and T1 is equal to 1. So this is the mod 8 up synchronous counter using T flip-flop. Thank you very much for watching my video. Please do like and subscribe to my channel. Thank you once again.